Good evening, students. This session we are going to look into the adjoint of a matrix. Adjoint of a matrix. Once again, we are dealing with determinants chapter, and we require always square matrices to be taken into our discussion. So we talk about adjoint of a matrix. So matrix is essentially a square matrix. I would like students to recall, already we have done what are cofactors. Cofactors, we know they are signed minors. They happen to be signed minors. In specifically, I can say capital Ij is minus 1 power I plus j of minor ij. So this clarity all students possess already. Now I am going to just demonstrate how to prepare the adjoint of a given square matrix. First of all, consider the matrix made of all the cofactors. For example, if we take a 2 by 2 matrix, we know there are altogether 4 elements. So 4 cofactors, and you can replace every element with the corresponding cofactor. That gives you the cofactor matrix. So let us see how that is done. Initially, let us consider matrix A, a 2 by 2 matrix. So consider 2, 5, negative 1, 4. Let this be the 2 by 2 matrix. So the task, find the adjoint of matrix A. Actually, the adjoint of matrix A, yes, there is a notation. There is a notation which represents adjoint. It is A, D, J. In brackets, and you write A. Let us find cofactors. Let us list out the cofactors. What about capital A11? I know by default the sign is positive, and I have to consider the minor, leaving the row 1, column 1, as simple as the element 4 itself. And considering cofactor for first row, second element, by default there is a negative sign because 1 plus 2 happens to be an odd number, and we are talking about minus 1 cubed. And then we have to take the minor 1, 2. Minor 1, 2 is leaving the row 1, column 2. What I am left with is element negative 1, negative of negative 1 makes positive 1. And cofactor 2, 1. So again begins with default sign negative because of 2 plus 1 odd and minus 1 power odd happens to be negative. Let us write the minor of 2, 1. Leave the second row, column 1, I get 5. So the answer is negative 5. And I can prepare A22 as minor only of 2, 2, which is leaving second row, second column, I get element 2. So I got the cofactors of all the 4 elements. Now I can prepare matrix consisting of cofactors. I call the matrix cofactor matrix. Cofactor matrix. So let me give a symbol. Any symbol you can assume, as long as the matrix is represented by uppercase. So let me give the symbol as capital C, uppercase C, made of cofactors. So cofactors, every element is replaced with corresponding cofactor, which means A2 is replaced with A11, 4, 5 is replaced with positive 1, minus 1 replaced with negative 5, and 4 is replaced with 2. So in essence, what has happened, you will be able to see that every element we replaced with the corresponding cofactor. Well, we are ready to now talk about adjoint. So let us define. So adjoint of matrix A is nothing but cofactor matrix transpose. So let me just represent it by the C prime, C dash symbol. So this is transpose. So now we arrive at adjoint A, which is 4, 1 in row 1 minus 5, 2 in row 2. And I have to consider the transpose, and after transposing I get 4 and 1 in column 1, minus 5 and 2 in column 2. That gives the adjoint matrix of the given matrix A. In essence, what has happened? Shall we compare, and the students can, so that students can arrive at their shortcut for a adjoint of 2 by 2 matrix. You can see the given matrix is 2, 5, minus 1, 4. Watch the diagonal elements. The diagonal elements, are they not 2 and 4? And watch out the diagonal elements in the adjoint. You can find very easily the 2 and 4 diagonal elements, they got interchanged as 4 and 2. What else do we observe? The number that was 5 in position A12 has assumed a negative sign. So the sign has been changed. Similarly, in position 2, 1, the sign has changed. Negative 1 has become a positive 1. So in effect, the students can independently prepare the adjoint of a 2 by 2 matrix by adopting the same procedure. When I say adopting same procedure, meaning diagonal elements are interchanged in their positions, and the other 2 elements need a change of sign only. So shall we do one such example quickly? If matrix A is say 5, 3, minus 2, 4, write the adjoint of A. So I can immediately write the adjoint using the understanding or using the shortcut. What happened? What is the diagonal elements here? 5 and 4. I need to interchange their positions. So the diagonal elements are 4 coming in position 1, 1, 5 taking position 2, 2. And the other elements are there but with change of sign. So 3 has to assume negative sign, negative 2 should assume a positive sign. Thereby the adjoint now is 4 minus 3 in row 1, 2 and 5 in row 2. So that gives an easy procedure to write the adjoint of a 2 by 2 matrix. Well, it is not so easy when we come to a 3 by 3 matrix. We shall do the adjoint of a 3 by 3 matrix a little later. What I would like to highlight now is the properties of adjoint matrix. Adjoint matrix. The very first one, a matrix when it gets multiplied by its adjoint, it commutes. In fact, that means the order of multiplication doesn't matter. A times adjoint A is same as adjoint A times A. The result is determinant A times of I matrix. When I say I matrix of the same respective order to which A belongs. If A is a 2 by 2, then this is I2. Sometimes we represent I with a subscript 2 or subscript 3, okay, denoting that it is a 2 by 2 identity matrix or a 3 by 3 identity matrix. So A times adjoint A is adjoint A times A. This becomes a very important property. Then one more property. What about the determinant value of the adjoint of matrix A? Determinant value of this adjoint A matrix. Well, it is determinant A raised to the power n minus 1, where n happens to be the order of the square matrix. You will write 2 if it's a 2 by 2 matrix. You will replace with 3. N represents 3 in case A is a 3 by 3 matrix. So determinant of adjoint A happens to be determinant A raised to n minus 1. Or let me be very specific. If order is 3, then determinant of adjoint matrix is determinant A squared. If it is a 2 by 2, determinant of adjoint and determinant of given matrix both are same. As you can see, the elements are in their respective, the elements are interchanged, but the determinant value doesn't change. That can be verified by a determinant A given here the previous example and determinant of adjoint A right there in front of the students. You can verify the determinant value. Okay. So in case the order is 3, it becomes determinant A power 2. And the third property, very important property, we are able to arrive at the expression for the inverse of a matrix. Well, in determinants we have one more wonderful property. Determinant of A times of B matrix is determinant A times of determinant B. This is an interesting property. When determinant of a product of two matrices of the same order, you are taking square matrix especially, then it is a determinant A times determinant B. And fourth property, in case B happens to be the inverse of A, we know very well in case only when this is true, only when the matrix B happens to be the inverse of A, where B happens to be the inverse of A, and this is the definition we saw already in matrix chapter. Well, we already have a similar expression in property 1. Shall we repeat that? Okay, what is that? A times of adjoint A same as adjoint A times of A, and it is determinant A times of I matrix. Determinant A times of I matrix. Well, I want to somehow compare property 1 with property 4. The definition of inverse matrix, that's what I have written as number 4. So how do I do it? The right side is I, the determinant A. I would like to, determinant A is a scalar quantity, so I divide everywhere by determinant of A so that the value of the equation doesn't change. So what happens is A into 1 by mod A times of adjoint A same as 1 by mod A times of adjoint A times A is I matrix only. You can easily see when this will be true. When this will be true, if I consider 1 by mod A of adjoint A as replacing B matrix, AB is same as BA is equal to I matrix. So comparing these two expressions, B, which is inverse of A, is same as 1 by mod A times of adjoint A. So I can say the B matrix, the inverse matrix, is same as 1 by determinant A of adjoint A. That becomes a very important expression for finding inverse of a matrix. We have already, students know, we have learnt the process of finding inverse of a matrix using the method of row operations from matrix chapter. Now you find this is another brilliant method wherein you don't have to apply any kind of row operation, but merely by evaluating the adjoint of A, you are in a position to arrive at the inverse matrix. So this is an important conclusion, and in fact the students will be making use of this expression widely, and we will be able to solve equations, a system of linear equations using this expression. We are going to see that shortly. In the meantime, let us work out a few of questions presented in NCERT. Okay, a very basic question let us take. Verify, this is I'm taking from exercise 4.5. Verify A times adjoint A same as adjoint A times A, and it is determinant A times of I. If A is 2, 3 minus 4 minus of 6, okay, so that is easily solvable because it's a 2 by 2. Given 2 by 2, you can directly write its adjoint matrix by swapping, interchanging the diagonal elements. 2 and minus 6 are the diagonal elements, which after interchanging it becomes minus 6, 2. The other elements 3, negative 4, the sign has to be changed. So 3 becomes negative 3, negative 4 becomes 4. Now let us calculate the product A times adjoint A. So how do we do that? The routine procedure of multiplication of matrices we need to complete, meaning the row 1, column 1, we do the product pairs and accumulate the sum, present it in 1 1 position. So 2 times of minus 6, negative 12, plus 3 into 4 plus 12. I am writing there one below the other. Next, 2 times of minus 3, negative 6, 3 into 2, positive 6. Done. Second row, first column, negative 4, negative 6 makes positive 24. Negative 6 into 4 makes negative 24. And in 2 2 position, second row, second column to be multiplied, my negative 4, negative 3, 12, negative 6 into 2 becomes negative 12. So we can see it gives as a result a null matrix. As a result, what we get is null matrix. Fine. Let us verify the case when when we change the order of multiplication, adjoint A times of A. Well, so we are writing up front -6, -3, 4 and 2. A matrix 2 -4 in column 1, 3 -6 in column 2. We can write the product, accumulate the sum easily. Yeah, -6 into 2, -12, -3 into -4, +12 gives 0. -6 into 3, -18, and -3 -6 makes +18. So sum is 0. 4 into 2, second row, first column, 4 into 2, 8, 2 into -4, -8 also. So the accumulated sum 0. Second row, second column. So that makes 4 3s are 12, 2 into -6, -12, and accumulated sum is 0. So this verifies. You can simply say hence it is verified. That is A times of adjoint matrix same as adjoint matrix into A matrix. One more truth, fact you have understood here. The two matrices, none of them is a null matrix, neither A nor adjoint A, but the product is a null matrix. So probably the students can remember or store this as a ideal example where the two matrices are not null matrices. I mean, either of the matrices are not null matrices, but the product happens to be a null matrix. So we have seen the past CBSE questions in short answer. They ask you to provide an example because this is a fact. So they produce an example where you can consider this as a B matrix. Let us say neither A nor B is a null matrix, but there is a possibility of the product AB being null. All right. So just an added information. Thank you, students. We will meet again in the next session with a similar 3 by 3 matrix and the procedure for finding inverse matrix. Thank you.